It's
All
12.
right, I'm ready to go. Okay. Good afternoon, everybody. This is Rudy Shankar. I had a little bit of a problem getting on. I thought it was banned or something like that, but I'm back on air. So it's a great pleasure for me to introduce Melissa Milstrey, who will be conducting the seventh seminar of our series this fall. The title of the presentation is Powering Tomorrow, Commercial Nuclear Power Plant Modernization. A little bit about Melissa. She's a pretty well-known person here at Lehigh. She's presented at our seminar a few times, and so she's also a product of Lehigh University. I'm really proud of that. Can you hear me?
Yep, we can hear you.
Right. So a little bit about Melissa. After graduating from Lehigh in 2018 with a BS in chemical engineering, she started her job as an engineer at MPR Associates. MPR is a specialty engineering consulting firm which specializes in solving challenging problems in the power and energy, federal and health and life sciences industries. Her experience has been focused in the advanced and commercial nuclear power industries, and she has served as a project manager, a client manager, as an administrative supervisor, and the MPR Women in Nuclear chapter lead. So welcome, Melissa. The floor is yours.
Awesome, thank you. Excited to be back talking to the ESE seminar and to talk about a topic that I'm very passionate and excited about, which is nuclear power. Specifically, I'll be focusing on power plant modernization today. But before we dive into that topic, I'll give a quick introduction to myself and the company that I work for. A very high level overview of what is nuclear power and how does it produce electricity, and why it's important to keep the nuclear fleet that we currently have operating on the grid and operating safely and reliably. And then I'll dive more into what is nuclear power plant modernization, why do we need it, and then some more technical examples of modernization that's been ongoing in the industry. Then we'll kind of wrap it up with feasibility of modernization, with some enablers or things that help modernization progress, and some challenges that are pertinent throughout the industry, and then close out with discussion and questions that people have on the phone. So quick background about me. Professor Shankar already went through a lot of these topics. I'll give a little more detail. As he mentioned, I'm a fellow Lehigh alum, so I graduated in 2018 with a bachelor's in chemistry from Lehigh. I love my time at Lehigh. I definitely took advantage of all the amazing opportunities that the campus has. So in 2016, I was an Iacocca intern and got to do an internship, research internship in Malaysia at the University Technology Petronas. So I was doing some carbon capture research. Also did some research as at Mountaintop with Professor Schultz doing rheology tests and experiments. I was a member of the Tau Beta Pi engineering honors fraternity. And then some more on the fun side, I was an orientation leader, so an OL. I was on the Green family. I even have Green on today for that. And then I was a America Reads, America Counts tutor. So tutoring kids in the South Bethlehem community for all 4 years. And that was something I was super passionate about when I was there too. So ever since graduating, I've been working at my company since 2018 as an engineer. My current role is a senior engineer, and we do engineering consulting. And one of our main areas is in the commercial nuclear power fleet and supporting them. I also have some experience in the advanced nuclear industry, and a lot of my work has been focused on modernization, which we'll touch on today. So providing support to several different utilities, helping them figure out what different modernization improvements make sense for them to install based on their site-specific circumstances and those sort of things. And then also I've been working on a very hot topic recently has been power uprates. So increasing the thermal power of a reactor to increase electricity sent to the grid for an existing plant. That's a lot of plants right now are considering performing power uprates. So again, hot topic right now. And then also I've done a lot of plant technical support, which basically means if a plant is looking to perform physical modifications to their plant or needs help with like troubleshooting an emergent issue, like a pump seal leak or something like that. I've done a good amount of work there as well. Got a couple pictures of myself in the industry here. This one is I'm doing a walk down at a nuclear plant where we are looking to install some sensor technology, which I'll actually touch on later in this presentation, is online monitoring sensors. And then at the top here is I'm at a Dresden, which is a nuclear plant outside of Chicago. And I'm in the control room simulator in front of the control rod panel. Quick background about the company that I work for. So company's called MPR, and like Professor Shankar mentioned, we're a specialty engineering services and consulting firm. And what that actually means is we help our clients solve problems and challenging problems. We've got a really strong roots in the nuclear Navy. So our three founders of MPR were in the nuke Navy, and following the creation of MPR, they actually helped in designing and constructing some of the first nuclear plants in the US. So we have a very long, strong history in the nuclear industry, and a lot of our work is centered around that. We work in, like I said, power and energy, health and life sciences. So that's more on the medical device production and side of things. And then we also do some work with the federal government. So before I dive into, why we need to continue nuclear power and why continue to keep them on the grid and why we need to modernize in order to keep them on the grid, I just wanted to give a very quick overview of what is nuclear power and how does it work. So something that you guys have probably learned in your engineering classes since probably sophomore year of undergrad is about the Rankine cycle. Nuclear power plants are, based on the Rankine cycle, but the energy coming into that cycle is produced through nuclear fission. Fission is a exothermic reaction, so it's releasing a lot of energy. And that takes place when an atom, which is uranium-235, typically splits into multiple different fission products. And that creates a chain reaction. You can see here in the bottom figure what that chain reaction looks like. So basically a neutron will hit the atom of U-235, that splits into multiple fission products and also produces energy and 2 to 3 neutrons. And those neutrons can go on and continue that reaction in a controlled manner. It's important to note that commercial nuclear reactions are controlled, meaning that they are controlled via control rods and coolant and moderator effects to make sure that the heat does not the reaction doesn't go uncontrolled and overheat. So the electricity is produced through, in the diagram here at the bottom here, you can see energy is created that heats water to steam. Steam spins a turbine, and that generates electricity. So a quick snapshot of commercial nuclear power in the US. In the US, there are two main types of reactors, one being a boiling water reactor, or called a BWR, which produces steam directly, and the second being a pressurized water reactor, or a PWR, which produces steam indirectly. Again, these are the types of reactors that are currently operating in the US. There are other types of reactors throughout the world. So when I mean produces steam directly versus indirectly, a BWR, you can see in the diagram on the bottom left, the water that goes through the reactor core where the uranium is and the fission reaction is taking place is directly turned to steam. It boils and turns to steam, and then turns a turbine, which produced electricity. The rotor's turns, produce electricity through the generator and powers our homes. In a pressurized water reactor, there's an extra loop in which the water that goes through the core is does not directly turn to steam and does not directly go to the turbine. It heats up water in an additional heat exchanger called the steam generator, which then turns water to steam and turns the turbine. There's benefits and drawbacks of both designs, but these are very common designs in the US. So in the US, the NRC, the Nuclear Regulatory Commission, is the regulatory body that licenses reactors, so approved reactors being built and continuing to operate, and develops the rules and regulations around operation of nuclear reactors. And here's a snapshot of all the reactors that are currently in the U.S. First commercial reactors started up in the 60s, peaked at the highest number of reactors at being 112 in the 90s. And slowly some of those reactors have shut down since the 90s. So today there are 94 operating reactors across 54 plants. Some of those plants have multiple different units on site. And the most recent plant to come online is Vogtle Unit 4, which was just last 2 springs ago, so April 2024. And that Vogtle 3 also came online at just end of 2023, I believe. So a couple units have been built recently, but not, we're not increasing the number at a steady pace at this point, though that may change in the near future. The average age of the operating fleet is 42 years, so they're definitely aging and will need some modernization, which I'll touch on in some later slides. And nuclear power in general makes up almost 20% of the country's electricity generation, and an even larger proportion, I think it's up to 50% of overall carbon-free energy production in the US. So nuclear power is a great source of our baseload generation, meaning it's always on. So unlike wind and solar, it is always on, providing power 24/7. And an exciting thing about the U.S. nuclear industry is that there's a lot of interest right now in growing the nuclear fleet. There's I think plans to build 10 new large-scale reactors, so these PWRs and BWRs, in the U.S. starting construction by 2030, which is really exciting. And then there's plans for at least 3 reactors to restart. So there's a couple of reactors that had shut down due to mostly economic reasons in the 2010s timeframe, and they're actually up for restart. So they're going through the licensing process. So it's not only important to grow and build new large-scale and small-scale reactors, but also to keep the existing fleet online and keep those 94 reactors that are currently operating online so that they can continue to safely and reliably operate and meet energy demands. That's particularly important because energy demands are skyrocketing. There is increased electrification of electric cars, AI data centers that are just increasing power demand, and then the grid is looking to decarbonize with a goal of 100% carbon pollution-free electricity by 2035, which is a dramatic increase from I think it's about 42% where we are now. As part of that decarbonization goal, there's the scheduled closure and the recent closure of several coal plants, or a lot of the coal plants in the US. So we have a decrease in the amount of electricity going to the grid with these coal plants closing, and a sharp increase in the electricity demand. So we need to, those are working in different directions, so we need to make up the difference and produce power in a different way. Nuclear is definitely part of, in my view anyway, at least part of that solution for increasing energy output while meeting those climate goals. And this is a US projection. It's outdated, so we can only imagine that the energy demand, electricity demand in the US is going to be even higher than what's modeled here. But it does show a good breakup of what we expect the largest contributors of that electricity demand to be in the industrial, residential, commercial, and transportation fields. This graph shows another snapshot of the world's energy demands. And I had actually given this similar presentation in 2023 to the ESE seminar. And I was just comparing what that graph looked like in 2023 to now. The 2050 energy demand total has increased 10 to 15% even since 2023. So energy demands are increasing at a lot. It reiterates the importance of having that baseload power. Keep the lights on. Okay. So now to get to the sort of the meat of the conversation today, I wanted to talk through what modernization is and why it's important to keeping the nuclear units online. Modernization is the use of modern technology and processes to improve operations and maintenance, everyday activities. Modernization of industrial assets has been, taking over industrial plants and energy production. So you can think about cobots and other robots are being used in assembly lines in the industrial industry. You have automated drilling rigs that are being used in the oil and gas industry. So things are being modernized. They've been being modernized for the last couple decades, but the commercial nuclear industry has been modernizing at a slower pace. So it's important to get the modernization technology that is available in other industries and bring it into the nuclear fleet so that they can stay cost competitive and reliable. So modernization, the definition up here is pretty broad, but it can really take a lot of different forms, some being physical plant modifications. So going and actually touching the plant, things like digital upgrades, equipment monitoring, so putting sensors on equipment. But there's also asset management and more on the business side that is not actually physically changing the plant. So that would be things like business process improvements, using iPads instead of paper around the plant, or using artificial intelligence to predict different outcomes or help with project management and those sort of things. So I listed out a couple different examples of different sort of groupings of modernization improvements that are currently being deployed at nuclear plants. And we'll touch on a couple different ones more specifically today. So some of the drivers for modernization, like I mentioned earlier, the nuclear fleet is on average 42 years old. So a lot of the equipment that was originally installed is becoming obsolete. So it's becoming outdated and no longer used. So it's really hard to find replacement parts, and it's very hard to find expertise. So the people that have the ability to maintain those systems are retiring from the industry and no longer available to provide support for some of these different systems and components. So as you replace those components, it can, with newer technology, there's more support and spare parts available. Another driver is O&M costs. Nuclear is a relatively expensive form of energy due to complex systems, high regulatory costs, and the requirement of having really highly trained personnel staffing the plant. So any way that you could reduce O&M costs for nuclear would make it more cost competitive with other generation sources like natural gas and coal. And the last one is climate goals, both on the state and national level. There's a lot of decarbonization efforts ongoing. And so keeping the fleet online helps drive towards those decarbonization goals. Some of the overall benefits of modernization, more efficient use of labor. So if you can automate a process, it frees up those highly skilled and trained personnel to go do other tasks on the plant. You can also increase the reliability and plant performance, and then also improve personnel safety. As an example, if you can, instead of using a manual inspection, you can use a robot or something similar to perform that inspection. That can improve personnel safety because you're not sending a person into a potentially contaminated or radiological zone. And safety is definitely number one on a nuclear plant. There's a really strong safety culture within the nuclear industry. Okay, so now I'll talk through our first sort of subtopic of modernization, which is robotics. You might have seen this guy here. This is called the Spot robot. It's a Boston Dynamics robot that has been very popular and in the nuclear industry and beyond. Robots can be used as an alternative to manual methods of doing things on the plant. Manual being sending a person in to fix a pipe or do an inspection, take a round, those sort of things. Robots have been used for the last 50 years in nuclear applications. Actually, since TMI2 in the 70s, nuclear has been using robots, but they've really increased their usage over the last couple decades, especially as the robotic technologies themselves have advanced. Nuclear has been more comfortable with implementing them. And as I mentioned earlier, robotic implementation is really useful where it's a part of the plant is either not accessible by a human or it might be dangerous to or hazardous to have a human enter that area. So there's various different types of robots. Just put some pictures here to see what sort of things are being used in nuclear plants today. It's really important to pick the right type of robot for the right job. So there's different benefits to each. Like as an example, a wheeled robot, as you can imagine, can move a lot faster than a tracked robot, but can't kind of traverse rough terrain. So a tracked robot would be better if you have a rocky terrain where you need to be able to move something. And a wheels application would be better if you just have a flat surface. The legged robot, it's a sort of like a walking robot. They call them like the robot dogs, which is similar to the Spot robot that was on the last slide. Those are all the ground-based robotic vehicles. The top and at the bottom, we have drones, which are flying robots, and submersibles, which are underwater. So these robots can be either remote controlled by a trained operator, or they can function autonomously. So you pre-plan a route and will send the robot through that route. Many robots contain sensors for obstacle avoidance, so to keep them from running into anything. And oftentimes what makes a robot useful is its payload. So the payloads are pretty much attachments that go onto the robot and serve a function like a camera for taking pictures or videos, taking measurements to create 3D maps, arms or grippers to perform physical tasks. So you can see the Spot at the top here has an arm payload and it's holding on to some sort of tubing, could move things. And then also non-destructive testing equipment for inspections. Think things like ultrasonic detectors for cracks or radiographic testing for weld inspections. So it's holding on to something to do a task. So the most common current use case for robotics is visual inspections and testing in those hard to reach areas. Some other tasks or use cases that are becoming more prevalent are maintenance activities, rad monitoring, surveillances, and then physical task execution, which is maybe turning a knob or cutting a pipe. And down here, just put some examples of current applications in the nuclear industry. This is a containment dome, which is a very large, like 100 to 200 foot concrete dome that needs to be inspected at some regular interval. Traditionally, people would use scaffolding to build up scaffolding to be able to physically climb and perform those inspections. But using a drone, you can remove the need for that scaffolding and just perform that inspection remotely. One in the middle is this is a Spot robot that's going in and can perform a routine radiation survey. Our radiation protection personnel on site have to perform routine surveys to get an idea of what the radiation map looks like on site. So you can send a robot in with a payload, a radiation payload, to perform that mapping instead and save personnel dose. The one on the right here is a submersible, or well, that's a scuba diver. But in theory, you can use a submersible to perform inspections of the intake. So for a nuclear plant, you have a lot of water that's coming in to cool down the plant systems, and the intake needs to be inspected at, again, a regular interval, and also cleared out of different things, different debris, aquatic plants and those sort of things, to make sure that the water can get into the plant. So submersibles can be used as an alternative to having divers go in and perform those tasks, which is definitely advantageous because diving can be dangerous, and it can also be very expensive. I'll go through this slide quickly. I know we talked about a lot of the benefits already, increased personal safety from industrial and radiation hazards, reduced costs, so eliminating manual labor and also preventing unplanned outages. This is an interesting one because if, say, you need to go check on a leaking pipe that's in containment, you're not able to really, you might need to down power or turn the reactor power down in order to go in and perform that inspection. But if you have a robot that can go do that job instead of sending a person in, you would avoid that down power, which would save a lot of money. As like a metric that's usually recited in the nuclear industry, it's an unplanned down power is about $1 million a day in lost revenue. So being able to prevent an unplanned outage is a very big deal. And then also when you use robots for these tasks, you can actually improve the execution of the task itself by increasing the quantity of data collected. Robots can stay in different zones for longer, so they can collect more data and better data often. And then it also provides for that flexibility and deployment, as I mentioned before. Being able to send a robot in rather than having a person come in can eliminate the need for those down powers, is a flexibility example. There's a couple different challenges associated with robots as well that are being overcome in the industry. Cybersecurity, so making sure that any data that's transferred over wireless connection is secure and properly segmented is extremely important. Collision risk, don't want your robot to run into anything. A nuclear plant has a lot of sensitive equipment, as you can imagine, so you don't want your robot to run into anything, which is where trained operators and the obstacle avoidance sensors comes into play. Big challenge for performing routine rounds is the line of sight requirement. So the FAA has a requirement where the operator needs to have a direct line of sight with the drone at all times for outdoor operation. So that really, it's kind of not possible right now to perform those outdoor autonomous rounds with a drone because a trained operator must always have that line of sight on the drone. And the last challenge I'll talk through is radiological controls. So say a plant just bought a very expensive spot robot. You don't want to send it into a radiological zone and then have it become contaminated in a way that you can no longer reuse that robot in a different zone. Okay, move on to the next modernization topic, which is online monitoring. So operations personnel will routinely walk around the plant and collect different data from different pieces of equipment. So there's an opportunity to modernize this very manual process with what's called online monitoring. So using permanently installed sensors to acquire data like temperature, pressure, vibration, and then that's being wirelessly transferred over to a central process computer to process and trend that data. I think of the online monitoring as, a Garmin or an Oura ring that you wear that's providing you with continuous health data on your body. This is basically doing the same thing, but for pipes and pumps, motors, heat exchangers within the plant. So it's continuously providing data to a central location. So that data is sent to what's called a monitoring and diagnostic, or M&D center, where trained analysts can see if the data is going out of bounds potentially, and then they can dig into what's actually happening and is this something we need to go change something in the plant to rectify. AI is most commonly being used in the online monitoring space at nuclear plants for advanced pattern recognition. So looking through all the data points that are coming in through online monitoring sensors and identifying different trends, and then developing predictions for equipment health. This is really important to help with risk-informed or data-informed decision-making. So helping to set outage priorities. Nuclear outages are very short amount of time. Like I mentioned earlier, you want your outage durations to be as short as possible so you don't lose potential revenue. And you're trying to get a lot of work done during that limited time. So you need to prioritize what gets done. So having the data available that tells you what equipment might need help or might need to be looked at and prioritized is very helpful. Can also be used for a transition from time-based to condition-based maintenance. So a lot of equipment is inspected currently on an interval of, every 1 year to 5 years, 10 years, whatever it is. But if you have more regular data, you can change from that time-based requirement to a condition-based requirement. So just inspecting when something needs to be inspected based on its actual condition. Some of the benefits of online monitoring, you're reducing the manual walk-down labor that operators are going and doing on a daily basis or a bi-weekly, whatever it is, basis. You can extend intervals and touch the plant less, which can reduce risk of touching the plant, potentially causing an issue. And then also increasing your awareness of of your equipment health can help to provide early indications of any issues, so you can fix a problem before it becomes worse or potentially fails. Some of the challenges, some of these overlap with robotics, like cybersecurity. Another one is wireless bandwidth. Not all nuclear plants have bandwidth throughout the plant, like wireless throughout the plant. And those are very important for a wireless sensor to be able to connect to the Wi-Fi. And a very interesting challenge unique to online monitoring is you're collecting a lot of data, but having data and not doing anything with it is not, I would not say that's a modernization. The idea of collecting data and using it to benefit your plant, change to condition-based maintenance, that is very important. So bridging that gap between just collecting a bunch of data points and actually doing something with it and making decisions is definitely been a challenge, but something that plants are working on. Okay. So next sort of subtopic of modernization I'll talk through is digital instrumentation and controls, or digital INC. So INC, I don't know if any of you guys were also chemies and took the controls class. It's basically how you measure and control process variables throughout the plant. So think temperatures, water flow, level in a tank, those sort of things. The nuclear fleet built in the 60s, 70s, and 80s largely has analog control systems. These components are aging and a lot of them are obsolete. So there's a need to upgrade these components and an opportunity to modernize to digital INC. Digital INC has been very widely reused over the last couple decades in other industries, and more recently have been incorporated into the commercial nuclear sector as well. I'm actually working on a project right now with a plant who has a turbine control system that's an original piece of equipment and it's obsolete. So their OEM or original equipment manufacturer no longer supports having spare parts or equipment like expertise. And so now they need to, and there's maybe less than 5 people in the world who know how to operate this system. So that is a huge risk to the plant. If something goes wrong with that system, there just isn't a spare or a person who knows how to fix it. So replacing that system is really critical to making sure that that plant can continue to operate for the next 20 to 40 years. Some of the benefits of digital INC, like I mentioned, the obsolescence risk is a huge one. So that's the availability of vendors and components. Self-diagnostic testing is interesting, so you don't need to go and perform like an invasive manual inspection of the asset every time. You can just have it do a self-diagnosis and tell you what's going on. There's also more flexibility with software upgrades, so you can perform updates more regularly on the system. Some of the challenges, first being is cost. It can be 10 to hundreds of millions of dollars to upgrade a system from analog to digital. Cybersecurity, again, it's a big one, especially when you're dealing with process equipment. Any hacking risk or anything that could give someone else remote control of a plant is obviously needs to be protected against. So rigorous cyber protocols with secure networks, proper segmentation is key. And then licensing, so that's updating your license with the regulator for new equipment. That can be a long process, so just making sure that you're working with the regulator and folding in any operating experience from other plants is really important as well. Okay, so some kind of new and upcoming improvements I'll just touch on quickly here. First being is advanced fuel. So there are a couple different demonstrations of different fuel forms than what has traditionally been used. There are demonstration cycles in plants right now, but full deployment has not yet taken place, I believe. So there's plans for full deployment as early as next year in the commercial fleet. Couple different types of advanced fuel, one being accident tolerant fuel or ATF. So ATF, new materials are added to the fuel pellets and cladding layer that produces a fuel that helps to prevent fuel failures like cladding rupture, pellet cracking. It's more corrosive, resistant to corrosion. Basically helps make sure that your fuel does not fail. And another advanced fuel type is fuel with a higher enrichment. So increasing enrichment from 3 to 5% to 5 to 6%. So that basically increases the amount of fissionable U-235 content within the fuel and allows for longer fuel cycles. So a typical nuclear reactor has a refueling outage every 18 to 24 months. And during that outage, about a third of the fuel is replaced with new fuel. But the advanced fuel, the higher burnup fuel, allows you to increase the amount of time before you need to refuel. So you extend your outage interval for those refueling cycles. And you get more energy because you have to shut down less frequently. Another hot topic in the industry right now, and the world in general, is AI. I know AI itself isn't new, but there's been recent advancements has driven up the usage of AI, a tenfold, probably more than that, over the last couple of years, both across industry and just personal life. So the nuclear plants are working to figure out the best ways to incorporate or integrate AI into the work that they're doing or the way that they're doing work. And then some ideas for things that are currently being done or might be done soon are listed here. Big one being data analytics and visualization. This is the advanced pattern recognition models I talked about in a couple of slides ago. So integrating online monitoring, so getting data and being able to use AI to read the data and do something with it. Another great use case for AI is performing operating experience searches. So historical plant and industry data repositories can be searched to see, hey, has someone else had this similar issue, or has someone else performed this modification before that we can learn from them. And then streamlining project management and admin work. That is a great use case for AI that's been applied. I would say it's not nuclear specific, but it would be great to apply that to the nuclear field as well. So switching gears, those were the sort of topics I wanted to talk about in terms of specific technologies for modernization of nuclear power plants. Now I wanted to talk about how and why is modernization feasible, some enablers of modernization. Having a longer plant life definitely enables modernization. So a lot of the plants in the US are looking to operate for longer, especially in the last couple of years. Like I said, there's been more recent favorability of nuclear power plants in the US. So having a plant operate for longer helps make the business case for making those larger investments in your nuclear plant and performing those modernizations, since you have a longer time to recoup the costs and reap the benefits of those modernization improvements. There's also been policy that's been passed recently that both promotes longer life of the nuclear plants and then also provides more capital that plants can go spend on investing in the plant. Some examples are the IRA and OBBBA provide tax credit incentives for nuclear power. So they're specifically, and this is something I've been working on, is the 45U tax credit provides existing nuclear power with a credit just for existing generation. And there's some other tax credits in 48E and 45Y, which provide new megawatts that are being added to the grid. It provides tax incentives for adding new megawatts. So these are great tax credits that are incentivizing nuclear and other energy technologies. There's also some initiatives from the DOE that are very specific to innovation, like the Light Water Reactor Sustainability Program out at Idaho National Lab in Idaho, help to fund nuclear advancements. So things like how do we produce hydrogen from nuclear power and things like that. A couple other enablers are industry peer groups. The nuclear industry is, I'd say, a pretty tight-knit community where there's a lot of intersharing between the different units and different utilities to help promote nuclear across the US. So going to an industry peer group and learning about what sort of more modernization technologies that other people are implementing and what's been successful and what's been less successful has been a big part of modernization being successful. And then also there's advanced nuclear power technologies that are looking to come online in the late 2020s. And a lot of them are being sited on current nuclear plant land. So there's an opportunity to sync what's going on in the advanced nuclear space and the sort of technologies that they're implementing with the existing fleet. Like as an example, they are, the advanced nuclear fleets are looking to do some automated licensing applications and integrating AI into licensing applications, and that could be transferred over to the existing fleet. And of course, there are some challenges to modernization. Number one being competing plant priorities. So say your plant has an issue with a pump and that is keeping them from operating. There's only so much money that the plant can spend. And if this pump is keeping you from operating, it's a pretty easy business decision to go fix your pump rather than go and modernize something and buy more iPads to modernize. So competing plant priorities is a challenge to getting modernization activities across the finish line. Costs, which we touched about, and licensing, and then personnel resistance to change, that's more on the cultural side. So that is any hesitation to take on changes or risks at the plant. So communication of, hey, why are these modernization improvements important is key to helping with that potential resistance. And then some general challenges to nuclear power also inherently impact modernization. One being workforce availability. There's a lot of SMEs or subject matter experts in the nuclear field are retiring or leaving the industry. And that's coupled with a very high demand for nuclear staff at the moment, between the commercial industry and advanced nuclear. So there's just a limited workforce to go forth and do all these cool things. So it's a good position for you guys to be in the ESE class to get to be a part of the energy future, because there's definitely a need for the workforce to grow. And then public perception, mentioned this a couple of times, but this has definitely shifted over the last couple of years, even just while I've been in my career in the nuclear industry. There's been a shift, but public perception of nuclear has changed over time. Sometimes people are not as supportive of nuclear, which can cause issues with keeping plants online. The good news is there's recent polls as recent as 2024 that show about 2/3 of people in the US are supportive of nuclear and want to see more nuclear be built. So that's great. In terms of public awareness, I also wanted to include here a couple links and resources for people to learn more about nuclear technology, careers in nuclear, facts and fictions and myth busting about nuclear, and also ways to advocate for nuclear. So can send up these links after the presentation. Couple of different organizations listed here are NEI, Nuclear Energy Institute, which advocate for nuclear policy and provide industry guidance. Nuclear Matters is an advocacy organization that increases public awareness about nuclear. The Women in Nuclear group, like Professor Shaker mentioned, I'm part of the WIN group. I'm actually our chapter lead at our company for Women in Nuclear, which is a professional organization supporting women in the nuclear field. And then the American Nuclear Society, or ANS, it's another professional organization for nuclear professionals. So a lot of resources out there to learn more and get excited about nuclear. That's the end of my discussion here, but wanted to see if there was any questions, thoughts, anything like that.
Hey, very good, Melissa. So we'll go into the question and answer period. And what I would like to do is, first of all, solicit questions from students in the audience. And students, when you ask your question, please introduce yourself, unmute yourself, and ask the question. So once we complete the students' questions, I will ask questions from the general audience. So if you don't mind unsharing your presentation, Melissa, so we can see everybody. Good, thank you. All right, questions from students.
Hi, can you hear us? You can turn it down.
Yeah, you're all you're like echoing because I think everybody's got their speakers on or something.
Yeah. Yeah, we're having some like technical stuff over here. Anyway,
They can hear.
Yeah, that's better. Whatever just happened.
Okay. Who has a question?
Okay. Hi Melissa, my name is Bintu Sina, and I'm a student in the Energy Systems Engineering program. Thank you for your presentation. It was quite holistic, but I have a lot of questions though. Okay, should I ask it in a row or I'm asking and then you?
Why don't you just start off and let's see where it goes, okay?
Okay, cool. So my first question is, while talking about operational and maintenance modernization, you talk about the transition between time-based maintenance to condition-based maintenance. So I was wondering, what about proactivity? Because just checking the machines where they need to be checked, is it part of operational excellence, or how do you combine both?
Yeah, and that's a really good question. And I think that transitioning from that to a more routine data collection using online monitoring actually supports what you're talking about and being proactive, because you get data at a more frequent interval than you would if you had to go in and manually inspect it at a 1 year or 3 year interval. So you have a better understanding of what your equipment health is at a given time, rather than just a snapshot in time. So I think that actually helps meet both the goal of being proactive while also balancing being financially responsible and having not going and inspecting things that don't necessarily need to be inspected.
Okay, I see. Also, there are some ongoing discussions about extending the license period to 100 years for the nuclear industry. Do you think that this modernization will help in that path, or it is too long of time for a license period?
Yeah, and I'm glad to hear that it sounds like you know a little bit about like subsequent license renewal and going from 40 to 60 to 80 years. So I guess to give some overview of that, nuclear reactors are licensed for a given period of time, and then they need to be, basically their license needs to be re-upped by applying to the NRC for what's called a license renewal or subsequent license renewal, or SLR. And several nuclear plants are starting to think about life to 100. And that's 100 years of operation. So I definitely think the modernization technology will help in some technical aspects. So some of the modernizations that I talked about are like physical plant changes. So taking equipment like a control system for the digital INC space and modernizing it to make it sure that it can last for longer. So I think that modernization and subsequent license renewal definitely go hand in hand.
Okay. And for my last question, wait, what was this? Well, I wanted to know, maybe I missed it during your presentation. What is the reason why modernization is slower in nuclear energy than in other sectors?
Yeah, that's a great question. So one of the things I talked about at the end in terms of challenges for modernization is part of it is resistance to change. Part of it is cost. And there's a myriad of other reasons, but those are two I'll focus on. Resistance to change being just like a cultural resistance to any increased risk. And safety is number one in the nuclear industry. We don't want to do anything that increases risk at the plant level. So there's some hesitancy to take on newer technologies until it is well understood in other industries and is well kind of like hashed out. Now that the technologies that we're looking to implement in the nuclear industry are well understood, there's some more openness to adopting it. But that needs to be properly communicated throughout the nuclear industry to make sure that people are open to implementing it. Another piece being the cost aspect. Nuclear is more expensive to operate compared to things like natural gas and coal. You need to hire a lot more people to staff a plant compared to a coal or natural gas plant. That being one main driver. So not having that extra capital is limiting for modernization technology, which is more or less discretionary spending. So if you don't have the capital to go and spend on modernization, you can't do it. Those are the two big ones that I see as the reason it's going slower.
Okay, thank you so much.
Thank you.
Thanks.
Right. My name is Lena. I also have a couple questions. So first of all, you mentioned how that the maintenance is usually on a regular basis, but that could change. I was wondering if the maintenance currently is like a regulatory thing that you must do it within this range, and if that would change if there's this modernization happening.
Yes, yeah, it is regulatory driven for some components. And the plants would need to go and get regulatory approval in order to change those inspection intervals that are regulatory requirements.
Okay, but that's possible.
Yes, there's a path for that and getting that approved by the regulator.
Wow, okay. And also, I've been seeing a lot about like big companies like Google and Microsoft pairing up with nuclear companies to build new ones for data centers and stuff. Do you see that happening at a more accelerated speed than how long it would usually take to build nuclear plants due to the administration and stuff? Or do you think that won't really matter that much?
Yeah, I think, I mean, this is my opinion, but But I think that having big investors that have the capital to spend, like Google and Microsoft, Amazons of the world, who have bigger checkbooks, that will help accelerate building new nuclear, or having power upgrades that get more megawatts on the grid. So I think, yes, it will advance the timeline that things can be built.
Interesting. But well, because I feel like a big part of it, at least from what I know, is like getting the approval for the design and then the licensing and all that. Do you think that won't change?
Yeah, so there's really good question. There's actually some Nuclear Regulatory Commission, so that's a regulatory, the regulator. There's some reform happening to help improve license approvals quicker. So traditionally, I don't know the exact amount of time. I think it's, hey, a license could take 2 years to get approved through the NRC. That's being truncated down to, we're going to try and do something between 12 and 18 months. I don't know the exact month, but there are initiatives to try and streamline the licensing process to make it quicker.
Interesting. Okay. Thank you. Thank you so much.
Well, thank you for presentation. So I have a question about supply chain challenges with some of the modernization things you were talking about, like robotics, for example, or just construction of a plant.
Yeah, supply chain, I'd say, is one of the top, like one of those hot issues right now in the nuclear industry, especially for big components like if you need to replace a turbine or a generator or something like that. That there is like a long lead time of 6 to 10 years sometimes, because everybody wants a turbine right now to increase the energy, because there's a lot of energy demand. So supply chain definitely needs to, I'd say, catch up to the demand for those bigger components. I'd say for robotics, there's not as much of like a lead time delay. So it's definitely component specific for supply chain, but it's a large focus point in the industry right now.
Thank you.
I have a question.
Is
Hi, my name is Eunice Kalzima. Thank you for your presentation. It was very interesting. The question I have is, I know that nuclear power plants are heavily regulated workplaces. What are some of the NRC standards and federal requirements that you need to go through if you want to work in some of those spaces? Because I understand just a degree is not enough.
Yeah. So it, again, depends on the job role that you're going for, but as an example, a nuclear operator who sits in the control room and operates a nuclear plant, they have to go through extensive training, years long training, and pass exams, and then go through sort of like shadowing sort of activities in order to be licensed. So that is for that role. I'd say for a general engineering role, believe you can, I don't work at a plant, but this is my understanding, is you can apply and work at a power plant with a general engineering degree, and you don't need special training or above that. But if anyone on the call is from a utility in the engineering department and wants to weigh in on that, that'd be awesome.
Okay, thank you.
Questions from students?
I actually have another one piggybacking off of Adam's supply chain question. I think I read somewhere how we're trying to start not depending on other countries for the fuel, the uranium fuel, as much. Do you see that happening in the industry, or is it mostly imported?
Yeah, it's currently mostly imported, but that you're right, and that there have been recent initiatives to increase our ability to make fuel in America. And I believe that some of the executive orders that came out earlier this year have been related to not only the NRC reform that I talked about earlier, but also making fuel in the US.
Interesting. And do you think, is that like equivalent to like fracking, or is there like another process to get it? I'm sure there's like a lot of safety involved with that.
Yeah, so it's called enrichment. So
Mhm.
you take uranium that's mined and you need to enrich it, which is kind of like a centrifuge process to increase the amount of U-235 content in the fuel. And the U-235 is actually that fissionable material that can produce the chain reaction that I was talking about earlier.
Okay.
But it's a large industrial complex process, essentially, that we would need to increase our capabilities for in the US.
Interesting. Yeah, I'm assuming it's very expensive. What are the benefits that outweigh that in doing that in the country?
I think energy security is a huge benefit for that, because if we're relying on only foreign resources for our fuel, and then we somehow get cut off, or there's a supply chain issue, we get cut off from being able to import, that could be a huge risk to having nuclear plants continue to operate.
Okay, thank you.
I have a question again. So I wanted to know, at what stage are these modernization tools at? Are they still in their early stages, or it has been around for a while?
Yeah, definitely depends on the technology that we're talking about. So things like online sensors and robots and digital INC, the three technical topics I covered in more depth, those are all being installed in nuclear plants now. And they're just increasing, like not on every single plant, but they're increasing their kind of implementation throughout the industry. Things like the advanced fuel, that is still in more the development stage. So that is still working towards full deployment. Things like, I very briefly touched on it, but there is something called the hydrogen electrolyzer, which is another sort of modernization technology that produces hydrogen gas. That's also in a more development stage. There's not actual, it's more demonstration models, not fully deployed. Things on the more business process side. So one example of a modernization on the business process side would be using an iPad for like work orders. So when you go in and do maintenance in a nuclear plant, you have to have a very specific work order that lays out what is going to be done, when, by who, all the information. That is a lot of times currently being done with a huge paper binder that's carried around. And now they're starting to transfer that huge paper binder to an iPad that can be carried around and filled out in real time and loaded up to a central repository for that information. Plants are working on that. Some have fully deployed it, but not all plants have. So depending on what technology is the modernization technology is, depends on where it is, sort of in its infancy versus full deployment.
Okay, thank you.
Great. Questions from audience? I'm sorry, student, any more questions from students? All right, I'm going to open it up to the audience. Please unmute yourself and ask the question. Or if you want to drop a question in the chat box, we can go through that. So the general audience, please have any questions from Melissa.
Rudy, it's John McCauley. Can you hear me?
John, loud and clear.
Okay. It says my video is disabled by the host. So thank you, Melissa. So on the what does it take to work on site? So I worked on two boiling water reactor sites after I came out of Lehigh in the late 80s at Limerick and Peach Bottom. And in terms of training, I guess the question was to be an engineer at a nuclear plant. So it depends on what your job responsibilities are, but the other things that you have to have before you get what it was called unescorted access at a nuclear site, you have significant background checks, psychological screening, drug and alcohol screening with random drug tests and that kind of thing because of the safety, national security concerns. My question, thank you, Melissa. So my question on obsolescence is there anything on safety systems that are obsolete? And like you described one that would be like a kind of an electronic controller. I just remember the for the BWRs, a lot of the safety systems were like relay logic and cabinets and stuff. I imagine it's the same.
Yeah. Yeah, the answer is yes.
Okay.
And there are some, I think at Limerick, actually, there's a safety related system, digital INC project that's going on, and I believe it's being funded by DOE as well.
Uh-huh.
So yes, and they're working on it, but as you can imagine, John, anything safety related is a lot more complex and requires a lot more regulatory analytical work associated.
Yeah.
It's not common that those safety systems have been upgraded.
Right. I mean, my first impression of the whole thing is these nuclear plants, especially the safety stuff, was designed in the 70s, although they were still building it in the 80s because of delays for other reasons. But I thought it seemed kind of antiquated to me at the time. But in hindsight, where we are today, I actually feel better about the whole thing because it's really not hackable, because all this logic is in it's all hard logic with relays. It's not computer based, so it's kind of a good thing that it's built the way it is now.
Yeah, I totally agree, and that's I think on every side, like the number one challenge is cybersecurity, and like you said, not being hackable. The issue is, I mean, with like the older control systems with the manual mechanical linkages.
Yes. Yeah.
I've been working on something like that for a turbine control system, and it's there's no one who knows how to tune that anymore, and who provides those spare parts. So
yep, I agree. Even back then, there was like people like, I just remember a guy from GE. He was like the Yoda of GE steam turbines, and he had to be flown in, and he's the kind of person that you describe the problem and he has 5 things in his head, and he goes and he says, well, did you shut this one valve? And it's like, oh no, it's open. It's like, that's what you need to do. And
if that guy retires, that's definitely
that's the problem.
Yes, exactly. And
thank you.
Yeah, John, I really appreciate your input on what it takes to actually get unescorted access and be able to work at a nuclear plant. I've been to quite a few, but I'm always escorted, so I don't know all the hoops that you have to jump through to do that.
Well, there may be more. I mean, this is from back to the late 80s, so I'm sure there's even more.
I'm sure.
Questions for Melissa?
Yeah, I do have one last question. I'm just wondering, I know that the US as of right now, it lacks permanent geological storage for nuclear waste. I remember reading somewhere about the Yucca Mountain project in Nevada. So I'm just curious if they're pushing any policies or what people are going to do in terms of storage of nuclear waste, because I think we cannot continue like this, and we're also considering building more in the future. So it means we need to start thinking about it as well.
Yeah, 100%. So can talk a bit about what the current fuel storage situation, what it looks like now, and what future plans are. So currently fuel is stored largely on site in what's called dry storage casks. So there are these steel and concrete casks that are stored and can, they're okay they're licensed up to 40 plus years, similar to a nuclear plant. They're regularly inspected and are, I would say, medium-term solution for waste. The US does not currently have that longer-term geological repository set up. The DOE is currently tasked with siting and figuring out where that repository will be located. Yucca Mountain was cited and then got canceled in 2010 due to political opposition and public acceptance issues. And so now they're trying to find a different spot. And what they're doing differently this time, my understanding, is trying to do more community consent-based strategies. So working with the community rather than telling them this is where the repository will be, but then rather working with the communities to understand why we need this, where should it be, those sort of things. So it's a work in progress. And in the meantime, we have a good medium-term solution. In terms of in the world, I believe Sweden, or is it? No, it's Finland. Finland has the repository operating. Sweden and France are working on that now as well. So it's again, work in progress.
Okay, thank you.
A great question.
Okay, there's a question in the chat box, Melissa, from Dylan. I need to draw. Oh, sorry. He's probably left the seminar. If you have any insight into the feasibility of nuclear fusion energy, is the fission industry involved in its development? How far away is the technology from being implemented in a grid scale power application?
Yeah, that's a very interesting question. So I can speak to it sort of tangentially. From some of my coworkers are doing some fusion projects currently. So yes, there is definitely a mix of people who are working from the fission industry and have transferred and started to do some fusion type technology work. So that again has to do with the workforce constraints that we have. People are working on fission, they're working on fusion, they're working on advanced reactors. We're spread thin. So if anyone's interested in nuclear, it's the time. So yes, fusion energy research has been ongoing. Currently, it's more in like the research and deployment, early deployment stages. So there's not like an actual fusion facility that's operating at this point. I live up in Massachusetts. So the one big fusion project up here is called Commonwealth Fusion Systems, or CFS, and I think they're working on getting a sort of a demonstration reactor in the early 2030s. But it's not actually going to be like a large scale production facility. So the research is ongoing. We're still 10 plus years away from having that connected to the grid, I think. But if there's anyone on fusion, doing any fusion technology on the call, definitely jump in because I am not a fusion expert.
Any questions from the audience?
Hi, my name is Tapiwa. I'm coming from Rice University, and thank you so much, Melissa, for the presentation. I think I would also piggyback off of the fusion aspect that you were talking about. I recently read of an innovation that's happening in China, of them exploring the fusion aspect. And I think the major challenge was they're still doing experiments. I think they do have plants in place, but it takes around 15,000 a day just to do that operation, which I feel like is very expensive. The article was really stating that they're still going into the research, they're still investing in it. But I think that's one of the challenges with fusion technology, because 15K is a lot of money, and for most countries to just comfortably engage with that, I think it's also a challenge. I was going to ask the question, but I'm glad it came before. I think that's why people are still focusing on fusion, but fusion looks like it's a better solution for the future. But yeah, thank you so much for the intel.
Yeah, definitely agree with your insights there. And supply chain is definitely an issue or a challenge for both fission and fusion. So a lot of complex materials are needed for the fusion research and fusion projects. So that's a ongoing issue there too.
Mm-hmm.
Thank you. Any questions? Thank you on this, Tapiwa, for asking that question. Anybody else with a question? Not, let me ask you a question, Melissa. So I remember from my early days, looking at crack detection using ultrasonic methods. The NRC was always very squeamish. I'm sorry, the plants were always squeamish about taking digital data, however, primitive it could be, because you're afraid the regulators would want to know what you do with the data. And so there's a general reluctance, and I remember looking at online monitoring, and that obviously was a great success, in the industry, which led to this power center, M&D diagnostic centers. Now, you mentioned about AI being applied for the nuclear industry. Does that have anything to do with data processing, or is it something different, or looking at regulations, processes, procedures?
Yeah, so, and I don't know if I'm directly answering your question, so you can fix my question here if I have it wrong. But I mean, AI, one of the biggest applications in nuclear now is digging through data to find any anomalies and then trend and predict what might happen. I think the most important piece of that is AI is doing the first dig and search into the data, but then it's being verified by a human. So a human is still reviewing what the AI is telling you and making the final call and making any decision making that touches the plan. So I think that's helpful in the regulatory space, because a human is still the last person, or what's actually controlling the plant. In terms of regulations, there's still a lot of open questions around AI and nuclear regulations, and the NRC, I believe, is still working on it. So I don't think there's any official guidance at this point. I'm not sure though.
Questions from the audience?
Melissa, one final question. I was reading on small modular reactors. I think it was an investment that was recently done in the UK, probably last week. And I was just thinking if it will be a good idea to build data centers with a small modular reactor. Do you think that's a good investment? Is it feasible? Does it make sense?
Yeah, and that's actually what some of the larger investing companies are doing, is building nuclear kind of like co-located with other industrial assets like a data center.
Okay.
Yeah, it's like a whole energy hub.
Okay, thank you.
Questions for Melissa? We've got a few minutes here, so. Here we go. There's a question in the chat box. Let's see. Oh, there are a couple of questions from Tom. What are some of the plant side perspectives or challenges to modernization of the interconnection with the utility? With modern digital protective relaying, there's more room for internal monitoring and safer, faster response using the fiber optic interfaces. Yet most existing interconnections are still using legacy copper-based wiring and electromechanical relays.
Yeah.
Listen.
Yeah, that's a good question. I'm not as familiar with the interconnection side. I do have some colleagues working on like grid modernization, especially as we have like, and this is tangentially related. I don't think I'm actually answering your question, Tim, but just like with distributed energy resources, so having solar panels or other small power inputs that are more distributed than traditional large power plants, there needs to be a lot of modernization of the grid and interconnections. So other people at my company are working on the grid modernization, but I'm not as familiar.
Yeah. Any last questions before we finish? All right, seeing none. Thanks a lot, Melissa. And
Really good questions.
oh, there was a question?
No, I was just saying those were really good questions that everybody had.
Yeah. All right. Well, thank you again. And so look forward to having you back again, sometime next spring or fall. And this is what the last seminar for this fall session will be held on December 2nd, I believe. December 2nd.
No, December 1st.
December 1st, sorry.
Yeah,
December
1st.
December 1st. And so it's been that'll be the 8th seminar. And I really appreciate all the speakers that have participated and all the audience that has participated. So we'll see you in a couple of weeks. And again, thank you, Melissa. Great presentation.
Thank you so much.
Thank you.
Thank you.
Thank you.
Thanks, everyone. Hey,
All
Rudy.
right. Yep. Well, that was good.
Yeah, it turned out pretty well.
Yeah, she got quite a number of people attending.
Yeah, I know. I was excited about that.
Well, she was a real trooper. She came in last minute and did a pretty good job.
Yeah,
Okay.